We'll be talking about wireless and wireline design considerations for better home and business connectivity products. It's a huge topic. Some areas might go faster than others. There's a huge amount of stuff to go over, so we'll just kind of go through it and see how the pace of the group is. But basically, I like engineering. What I'd like to point out is if any of you have an interesting topic for the Consumer Electronics magazine, I am now a senior editor of the magazine, so we'd love to have articles about your topics related to consumer electronics in the magazine, and I have some copies in the back. We'd love to have you take a look at that. I'm actually a distinguished lecturer for the Committee on RFID, Radio Frequency Identification, and that's what this talk I'm giving today is one of the distinguished lecturer talks from that series. As the old world passes in the new world, embedded intelligence and connectivity into virtually every device at a relatively low cost creates the reality of Internet of Things. People also call this the Internet of Everything. Cloud computing, IoT will enable convergence. The way we view data and ourselves will change. Autonomous mental devices, the beginning of AI, a truly smart home. RFID energy harvesting. We're going to talk about wireless, some antennas, some application examples. We'll talk about security and about 1874. The thing to remember now, we've had this vision for a long time that we're going to have our, I think the best example is if we remember cartoons, the Jetsons. We remember the flying cars, robot in the home that would talk to you and it would help enable you, and you didn't have to do the mundane tasks. We've always been shooting for that goal since the 1950s. And we're now getting closer and closer to that goals. And the people in the room, the people in the webinar are all going towards that same goal. How can we make our lives better? How can we simplify things in our life so we don't have to worry about it, we don't have to really think about them, they just happen. And they happen for the betterment of ourselves and the betterment of our community. And that's part of the goal of ITripleE, is advancing humanity through technology. And we're going to be talking about some of those technologies today and some of the pitfalls that can occur as you develop some of these new technologies. AI in the home. AI in the home. Smart home. This covers smart grids, security systems, home safety, computer security, cloud control, IoT, infotainment. It's a long list. The thing to remember is artificial intelligence we have to some degree already in the home, and it's starting to get bigger and better, and it's going to become more evasive, or pervasive if you prefer that word over evasive. Hopefully, if we do it right, it'll be a benefit for ourselves and not a hindrance for ourselves. There was a lot of hype going on for the I don't want to say non-technical, but not maybe in this field. They have a very negative hype about artificial intelligence. Stephen Hawking, I know he means well. Bill Gates means well, but for some reason he has all this negative hype on artificial intelligence. There's a lot of negative hype about IoT, Internet of Things. The reality is we've always had it, it's just getting better, and we just have to make sure we keep on the right track so it doesn't go down a bad track. Here's an example of Sonochan, a smart home. So Sonochan is the name of this artificial intelligence. And this artificial intelligence, to humanize it, looks at a lot of different things. She looks at the energy harvesting, maybe through solar panel. She helps control the Internet of Things, infotainment, home security. Helps with my smart car. As I plug in my smart car to the power grid, she helps with pest control, the home cleaning systems. She helps coordinate all these different things in the home. Interestingly enough, one of my research areas is artificial intelligence. And so I've been working on Sonochan for a few years now with some other colleagues of mine, Dr. Cornelis van Rensburg at Huawei and Dr. Larry Zhang at NVIDIA. And so we're getting closer and closer. So we have more and more things in my house. I have some active robots in the house. And some other active systems in this house that work with the artificial intelligence. And it learns and it grows with our family as it develops. Let's talk a little bit about energy harvesting, to cover lightly on some topics to get you aware of them. Energy harvesting, as we know, is not a new topic. Tesla came up with it way back in the late 1800s and early 1900s. And energy harvesting basically says we're taking this RF energy and we're converting it to DC, and then we're power conditioning it and going it to a load. Now this is very doable. The example here is the P2110 power harvester chip, which works at 915 megahertz. This can also work at 2.4 gigahertz. It can work at lots of different frequency ranges. But basically this energy that's coming is all around us. It can come down and you can reharvest it to things. So I imagine in the audience, people have cell phones. And my guess is your cell phones are turned on, not turned off. Hopefully they're in the silent or vibrate mode. But every one of your cell phones right now are emitting RF energy. What if we could harvest that RF energy? And how much RF energy are we talking about? Well, we're talking about Wi-Fi, and a Wi-Fi radio in a cell phone transmits normally at 15 dBm. You can recapture almost half a milliamp off of that 15 dBm, just from one cell phone. It doesn't sound like a lot, but with certain sensors, you can do a lot. Thing is the more phones we have in here, so you have another 500, you have 500 microamps, 500 microamps, 500 microamps. There's an interesting thing that occurs though with multipath. So if you take Maxwell-Clerk's equations and you take Nikola Tesla's equations of variance and resonance equations together, and a funny thing happens. If you take a phone that's doing 15 dBm of power, another phone doing 15 dBm of power, so you would imagine, okay, I'm pulling out 500 microwatts of power from this phone, 500 microwatts from this phone, but with the resonance equations, we actually get more than that. We actually end up getting 1.4, 1.5 off of two 500 microwatt sources. So we actually start seeing, because of a resonance effect, we actually start seeing more power. Actually, with Nikola Tesla's equations, you can get more than 100% derivation off of a single source of RF, which is very interesting to look at the equations. And that's the great thing. So if you're in a group of people with all this power coming off, you get all this power. There's all this power you can reharvest. So an interesting thing I mentioned here is one of my patents that are pending is adaptive antenna frequency modification. Long word. One problem we have with RF energy harvesting today is it's for one frequency. And so if you deviate from that one frequency, you're not going to get as much effective energy. So right now, like in this room, 2.4 gigahertz is pretty handy. That's Bluetooth, it's a lot of RFID, that's Wi-Fi, that's microwave ovens. There's a lot of stuff at 2.4 gigahertz. So RF energy harvesting for that is great, but what if you go into an environment where now we don't have 2.4? What if we have 5 gig now, or we go down to 800 megahertz, or at 60 gigahertz? We need to have a way for RF energy harvesting where I can have like an automatic gain control, where I can look at the RSSI values and change the different signal frequencies, kind of like a spectrum analyzer does, right? Look out in the air, see the energy, then reconfigure myself. And we can do this through gates. And we're just changing the FC sub O, so it's not that hard. Here's a slide showing some GSM power levels, the amount of energy you can reharvest off of them. RFID, really quick. RFID is radio frequency identification. RFID we see in toll tags, asset tracking, biometric sensors. There are a lot of Internet of Things with RFID, wireless sensors. Near field contact is another term for RFID. What is it really? It's just a field. There's a magnetic field that pops out. Magnetic field, there's a device that when the magnetic field hits that device, when the magnetic field hits through a coupled coil of wire, we have electrical charge that's developed. The electrical charge goes to a microprocessor, powers the microprocessor really quickly, and then it sends out information. Some people relate to this, the old IFFF systems, identification friend and foe, where it would actually send information back to say, this is who I am. This is the same idea really as energy harvesting. And RFID we now use in toll tags, we use it all over the place. Let's look at some of the ITripleE standards in home networking. ITripleE 1901 is a standard for broadband over power line networks. It's up to about 500 megabits of throughput. There's two versions of this. One version runs at about 100 kilohertz, another version runs at about under 500 kilohertz. Basically this runs on your AC power in your home or in your office. It sounds kind of science fiction, but it's actually been around for quite a while. This is a product from Insteon. They sent it to me just 2 weeks ago. I do a lot of reviews for the magazine. This system works through the power of the home. You hook up Insteon LED light bulbs in your home. You put this in the home. You hook it up to your television, and you can run all your Ethernet and control your lights and home automation security system without installing any Ethernet, without having any Wi-Fi in the home. It all just runs through the power of your house existing. So these are taking off. I was at CES this last January, and power line BPL is taking off in the industry. The interesting thing is it's not new. It's been trying to take off since about '98, and they keep trying to reiterate over and over again. They've had lots of different problems, early problems with doing Ethernet over power lines. was that if you came to a circuit breaker, as soon as it came to a circuit breaker and tried to jump the circuit breaker, your bandwidth would go 500 megabits down to 10 megabits. It was just a huge drop. So they started to insert OFDM encoding methods, which fixed that problem. So now they're past most of those problems, and now it's very viable and very usable. But this is interesting because the people that work on these types of technologies, they don't think about some of the other aspects, which we'll talk about a little bit later, like EMC, the type of noise we're working about. So now, normally a lot of you electrical engineers in the audience, we try to clean up our power as much as possible. When we see 100 kilohertz radiation, we try to eliminate it because we know it's going to cause us EMI, FCC problems later. So we try to get rid of it as much as possible. Now this particular standard is actually trying to use that frequency band on the power to be usable. So now we have to look at extra considerations of how do we still be able to use that for Wi-Fi and it not eliminate it and have extra energy coming out of our product, which might damage us later. Another one of these standards is ITripleE 1905.1. This standard actually says, okay, we have Wi-Fi and we have this power line. Let's work together. Let's use power line and Wi-Fi together. There may be times when we want our internet connectivity to go through our walls. There may be times when we don't want it to go through our walls, where we want it to actually go to some Wi-Fi device. Or we may have all these legacy devices that we're selling that are Wi-Fi enabled, and we want to have both. So 1905 says this is how we work together on those two standards. And then briefly, 802.11ac, this is multi-MIMO, 500 megabits to 6.9 gigabits. These are, it's one by one, which is normal, 1 by 1, 2 by 1, 2 by 2, 3 by 3, 4 by 4. That's a normal what we call MIMO, multiple input, multiple output to aggregate. We see that a lot now in the stores. But 802.11ac is taking off, and now we're seeing up to 8 transmitters. And in some cases, we're seeing up to 16 transmitters. So 8 and 16, you have 16 different antennas. So our throughputs are rising quickly. Because the home consumer and the office consumer, the more people we have in the office, the more people using internet on multiple devices, the more bandwidth we need. And this is a good bad thing, right? So we want to consume more, we want to have more. This normally means new equipment to support it all, which means we have to design more stuff. We all stay employed. Good thing. 802.15.4. This standard covers a broad mess of stuff. Zigbee, wireless HART, which is really popular in Europe, but you almost never hear about in the US. The MIWI specifications, there's a whole bunch of Bluetooth, there's a whole bunch of stuff in this standard. So here's an example of power line communication on the smart grid. We see 1901 through the power AC going to solar panels, light switches, security cameras in the home or the office, appliances. 1901 is actually specified in the smart grid standard. So the U.S. government, an entity of the U.S. government called NIST, National Institute of something or something technology, standards technology, has specified that 1901 and 1905 now be part of the smart grid standard. So this requires companies to implement 1901, 1905 for automotive technologies. So Tesla, they're trying to make sure they comply with this, charging stations, smart metering outside the home. An interesting thing to consider is we have 1901 going from your street to your home. So they're actually doing internet communication from the street to your home. Actually, up to a mile from your house, they're allowed to do 1901 to your home. The question is, how is their security protocol? What if someone hacks into that a mile away from your house and then can hijack and see your information? Maybe they decide they want to turn off the air conditioning to your house or change the temperature to your house. That could be a bad thing, especially in Texas. So 1905, as I covered before, this covers this whole convergency of technologies. That's what this picture shows. This would also, 1905 doesn't actually cover MoCA, which is a technology many of you may have been familiar with. MoCA is multimedia over cable. That's another technology that may be in the home. So these are all different technologies and how they converge and work together. Here's an example, a slide for 802.11ac, and this is here mostly for your reference. just to show you some of the high throughputs you get. One of the tricky things here in dealing with Wi-Fi vendors is they talk about, for example, here's an example, a 1x1 MIMO, which sounds funny because it's one transmitter, one receiver, and MIMO normally means multiple, more than one. A 1x1 max throughput's 150 megabits over the air. But to get that, you have to have a really, I always get this confused, but I think you need to have a 40 megahertz channel, and I think you have to have a 800 nanosecond guard band. And to do that, your router has to be able to support aggregation. And most routers do not support aggregation. Unless you're in an office and you buy a Cisco $2,000 router, does it support aggregation? So we find a lot of customers out there that wonder, they use a chip that supports 150 megabits over the air. It goes out into the customer field. The customer says, well, we're only seeing 75 megabits over the air. What's going on? And you talk to Qualcomm or Marvell, and they say, well, here's the routers we tested with, which are all expensive router, expensive router, expensive router, expensive router. So what are you testing with? Well, I'm testing with, this $150 or $49 router from Fry's. Oh, does it have aggregation? Well, no. Well, that's your problem. Well, you're selling to a consumer marketplace, and that's what they're buying. And so that's what you have to consider, is the numbers may not be apples to apples. They're probably apples to pineapples, right? So something to consider. Internet of Everything. This is smart plugs, smart appliances, refrigerators, thermostats, in-home displays. Here's an example of an IoT device. And this won't be too surprising. Most of the designers in the audience will realize we've had IoT for a long, long time. This isn't a new thing. It's just a new marketing term. Basically, an IoT device is something with a MAC address that can access the internet. And it passes information through the internet to the cloud. And what's the cloud? A whole bunch of computers out there someplace processing. Right? Another interesting term. Here's one from Broadcom, and this is their Wicked module, as they call it. And it does a bunch of stuff. It's funny, some of their examples was you could use this in a hot tub, an ofuro, or a toilet, a home security, a refrigerator. You can pretty much use it anywhere you want, and these boards exist and the APIs exist. Another example of an IoT device from Texas Instruments. Here is, let's see, is this Texas Instruments? Yes, Texas Instruments. So this is using Zigbee with an MCU, with some USB, and you can see at the tip of that device there's a onboard antenna. So that's another example. Design considerations. Things we have to consider are cost. Economy of scale drives bill of material. We'll talk about that. Frequency allocation. Think about your design and think about the frequencies they're going to be using in the home or the office, and maybe what frequency allocation is correct for you or your customer. Design for test and manufacturing. People designed it, they get it working, prototype, it's wonderful, then they go to build it in mass production, and they're shocked that it takes them 2 to 3 years to get through production because it works so well in the lab. And then compliance, testing, logos, FCC, CE. We never worry about this to the very, very end until the marketing guy says, oh, by the way, can I use the Wi-Fi logo on this? Can I have the USB logo on this? And then everyone scrambles and says, okay, how do we do the test to pass that? And it turns out we didn't implement a whole bunch of things we were supposed to implement in the very beginning of the design to get it to pass. Economies of scale. This happens a lot at O&S Services, the company I work for during the day. The company comes to us. Here is a bill of materials, which you may or may not be able to see, for I believe an Apple iPhone S. And the bill of material manufacturing cost puts this at about $218 for an iPhone S. This was back in 2013. So a customer comes to me and says, okay, I want basically this functionality in this other product, LCD screen, touch screen for a thermostat. And I see it's going to cost me $218, so I want you, O&S Services, to design this for us. It's going to be $218. We're okay with letting the price go up to $250 because we want this added bell and whistle. And I said, but you understand, though, this is for millions of units. This BOM cost is for millions and millions of units. And Apple is very aggressive on pricing, if anyone's ever dealt with Apple. So an example of this, we have a line, 1, 2, 3, 4, 5, fifth from the bottom. It's the wireless LAN, Bluetooth, FM, GPS chip. And it shows it here at $4.20. There's no way you can buy this chip for $4.26 unless you're buying it millions of units and you got a sweet deal through Apple. That part, generally everywhere, in 100 to 500 units is $42. Okay? At 100 to 500 units. At 1 unit, it's probably $75. So you have to remember this. If you're designing a product, think about economies of scale, because this always happens. They say, I want this, and I say, you understand, you're going to build 1,000 of them, right? Yeah, well, so instead of costing you $200, that's what, 10 times, $218, it's going to be about $2,000 for 1 unit in a 500 unit spread. You're going to make 1,000 of these? That's $2 million. Do you have $2 million? And they go, oh! So I sometimes feel as a consultant, my job is to make people feel bad and show how poorly they're going to die. That's probably why I don't get as much business as I do, probably. But things to consider. And this is just more of that second page for reference you can look at later. So that's something to consider. Frequency allocation. Which frequencies should I use? Should I use 2.4 gigahertz, 5 gigahertz, 60 gigahertz, sub-gigahertz? What frequency is a microwave oven? 2.4 gigahertz, right? Why is it 2.4 gigahertz? Because it happens to be the optimum frequency to make water molecules not oscillate. I got in trouble with a physicist once for saying this. To gyrate to generate heat. It's not oscillation. It turns out to be the oscillation frequency. I hope I get in trouble this time for salt crystals, though. So that's what I was told. The physicist was clear enough to point this out to me, so I will say that. So what's in most food? Water and salt. So it's great to heat that up. Why? By the way, why do we even shoot on that? Because during World War II, we found that 2.4 gigahertz radar was great for bouncing over water, over salt water, and it was great. And that's what we helped. It's helped the Allies win World War II. Is we used 2.4 for our radars in the military, and after the war they had all these magnetrons left over at 2.4 gigahertz. It was a natural precursor to moving to microwave ovens with all that technology. We've been using it ever since. So an interesting note is, what does Wi-Fi run at? 2.4 gigahertz. What does Bluetooth run at? 2.4 gigahertz. Some RFID, 2.4, upper end LTE, 4G wireless, 2.4. What's mostly in your brain? Water and salt. Interesting. Oh well. So you have to think, what frequency do you want to use in the home? Now a lot of people use 2.4. You may be using 2.4. And that might be what you have to use. And we'll talk about channel selection. There's some things you can do to help eliminate some of the problems in your home with 2.4. 5 gig is coming online. A lot of people are realizing 2.4 is really crowded. If you did a spectrum analyzer in this room right now, you would find massive amounts of 2.4 gigahertz energy in this room. Massive amounts, just from all the cell phones you guys have turned on. 5 gigahertz, there's not as much. 60 gigahertz, which is much less, and this is 802.11 AD. 60 gigahertz is going to take off an automotive radar, so that's maybe another field. And then sub-gigahertz. We meet a lot of people using 900 megahertz, 800 megahertz, and those bands, you actually get the law of physics. Lower the frequency, farther the distance. Higher the frequency, lower, shorter distance. So same thing. So we find a lot of people using non or proprietary technologies. Use 2.4 and 5 gig. There's lots of stuff out there. It's off the shelf. You can buy the chips. It's easy to design. You use sub-gigahertz. You got to put a little more effort into it. The software is more complicated. You got to write your own software. It's not all standardized. But you can go further range. You have less issues. There's a lot of great things. Wi-Fi. Which mode should I use? Wi-Fi direct, infrastructure, ad hoc, mesh. Infrastructure is the old, reliable, requires access point, limited range. Ad hoc mode is a point-to-point. And this is funny because these names come from engineers. It was developed ad hoc. It really wasn't a good plan in place for developing it. So it's point-to-point, but has very sloppy security. It's hard to set up for the user. Might be okay for the developer to set up, but for the end user it's hard to use. Wi-Fi direct, when they decided to spin out Wi-Fi in the spec again, they basically took ad hoc mode, cleaned it up, and became Wi-Fi direct. This is point-to-point, no need for an access point. Has pretty good firmware implementation. It's still very new. So this means your phone with Wi-Fi Direct can connect straight to a printer and send stuff straight to a printer. You don't have to worry about the access point. You don't have to worry about getting someone's SSID password. You can just do it. You have your product in the home, you can do Wi-Fi Direct right to that product. Miracast is similar to this. Miracast is kind of an Intel, Microsoft display consortium invention. It's basically Wi-Fi Direct. It's point-to-point, but it's for display. So Microsoft in Windows 8.0, 8.1, it now has Miracast built into the OS. So if you have any of the new Qualcomm or Marvell chips in there that support Wi-Fi Direct, with the Miracast protocol on top of it, your PC, you can Miracast it to your television, and you can, if your television supports Miracast, you can Miracast it to your television. It's a great thing. Action Tech ScreenBeam TX, a great little product. It should work wonders. We tested this. You plug it in, and you should be able to beam all the content from your laptop straight to your television set. Unfortunately, it doesn't work very well. The Wi-Fi is fine, but they didn't consider power considerations on HDMI. So they plug into the HDMI in the TV, so they didn't worry about the HDMI power considerations. So anytime there's a power fluctuation on the HDMI plug itself, it causes the chip to reboot and you lose connection. So we tried for about 8 hours straight to connect all over different office space locations to try to connect to the solution, and it was almost nearly impossible. We could see the signals with a Wi-Fi sniffer. We could see it was making the protocol just fine, but it just couldn't seem to ever finish on the connection. It kept rebooting. So they had some serious software issues. So you have to, some of these new technologies are great to work with, and your marketing guys might like the idea, but you really have to get the software down and your system down in place before you start selling it. So now Action Tech is having massive recalls on this product. And they've basically had to say, look, I guess we really can't sell to the open marketplace. We have to sell to maybe schools or hospitals, something very defined where we can tell them this is exactly how to do it, and we'll develop special software just for your system and control the hardware. Mesh, point-to-point. This is like a UDP, basically meaning it's broadcast. You broadcast all this information to all the different nodes that have mesh, and they rebroadcast it to everybody else. It's great. It's what Bluetooth was supposed to have been for Bluetooth 1.0, and then we messed up Bluetooth by adding security. And then it lost the mesh capability. So mesh is doing the same thing. It's just rebroadcasting everything. It sounds great, but very few chips out there support it. They say they have mesh capability, but they mean that you have to write your own firmware, but they don't want to release the firmware to show you how to write it. So it's a double-edged sword. So you find that it's very, very hard to implement mesh. Even in Linux, there's very poor implementations of Linux implementations to use mesh. So it can work if you have a good software team, but if you don't, it can be a real problem. Wireless channels, 2.4 gigahertz. One of my pet peeves is people design 2.4 gigahertz, and they use channel 11 as a standard channel. And this is because Broadcom, Intel, one of those guys at one point decided that the default channel for Wi-Fi for any of their chipsets was going to be channel 11. And they sold it to a whole bunch of people, and all those developers never changed the default. And a lot of those companies never gave the user the opportunity to change the default. So you can turn on a Wi-Fi sniffer in this room or in your neighborhood, and you can see that every Wi-Fi running at 2.4 gigahertz is all running at channel 11 around you. Everyone's running at channel 11. And so because of that, you start transferring stuff, and all of a sudden your bandwidth is blah. If you change to channel 7, channel 5, channel 4, you're going to go, oh my gosh, my bandwidth increased. Thank you, Verizon. Thank you, AT&T. It's not them, it's just your access points on the wrong channel. And everyone's doing the same thing. But no one wants to change it. So it's just amazing. So if you design a product, change for other channels. Same thing with 5 gigahertz. Everyone uses the same channel on 5 gigahertz. So here's a gotcha I want to make sure you guys hear about. The European Union has a set of standards out there for FCC, basically, that's not FCC, this is European Union, CE mark or SISTR test requirements for products. And it started this January, and it said that anyone using 2.4 gigahertz, you have to make sure that if you see 5 gigahertz out there, that you blank yourself. That's for radar. It's a radar blanking technology because they don't want to have any problems with the airplanes. Well, the problem is if you're a U.S. company and your product is ever going to be sold in the European Union, which is all of Europe, you have to comply with this. If you don't comply and you get caught, you have a 5-year ban of never selling to any company in the European Union, plus a €1 million fine. So if the €1 million fine doesn't wipe your company, the 5-year ban in selling in Europe will probably wipe the company. If you sell to any U.S. airplane manufacturers, you have to comply with this because their planes go to Europe. If you sell to any automotive companies in the U.S., you have to comply with this because their products go to Europe. If you sell anything in America that might happen to go to Europe, you have to comply with this, even though it's a European specification, not a U.S. specification. So I meet a lot of European companies who say, I don't have to worry about this, we only sell to the U.S. Well, as soon as one of your products goes to Europe, and how this works is the European Union doesn't check. Your competitors check. Your competitors see your product sold in the European Union, they buy it, they get the sales receipt, they test it, see it fails, they send a test report to the European Union and say, hey, these guys failed. And it's an anonymous test. European Union contacts you and says, show me a test report that says you passed EN 1.81 before this date. And if you can't provide it, they'll send you a bill for €1 million and they'll ban you for 5 years. So if you look it up, this killed Minolta. That's why Minolta died as a printer company. They got caught back in 97. Now it's owned by Konica Minolta. So if you look at my resume, you see I work for Minolta, then I work for Konica Minolta, because that's another thing you can do. You can wipe your company, rechange your name, and come back again, but I don't recommend that. So these technologies, these things you have to be aware of them. They're not hard to pass, but sometimes the chips you may be purchasing may not support that change. So, designed for test and manufacturing. One of my colleagues at ONS Services actually sent me some updated slides, but we weren't able to get it in here fast enough. But something to consider. I've hand soldered 10 boards. Now I need to build 10,000 units. Test time equals product cost. If you've ever worked at a very large company, you'll realize this. But if you work at a startup, you may not realize this. Wi-Fi can take 3 to 5 minutes. These things can take a long time, right? So if you work it out, we can see that a 16-minute test at 10,000 units, that's 332 man days. That's a lot of money. A 45-minute test for 10,000 units, 937 man days. That's a lot of money. You know, if you do the right DFTM and automation, you can reduce that test time that maybe takes 16 minutes or 45 minutes down to 3 minutes. And you can reduce the massive expense. You can basically cut your cost by 1,500%. Hopefully I got my numbers right, 15 times 100%. So, but you can save a lot of money by reducing your test time. Certification approvals, emissions. This just we'll run through this. You can take a look at this later. These are some of the certification approval costs you have to look at. Wi-Fi or logos. People forget logos cost lots of money. Are you required to have logos? No. It's purely a marketing thing. If you want it on your box, you should get this. If you put the logo on your box without it, you'll get a nasty letter in the mail, and they'll tell you that they'll ban you and they'll sue you in court. So, but do you need a logo? Maybe not. You just, it's just Wi-Fi. It just depends on your marketing guys. We want to put it in a box. So, one topic we want to talk about: external antennas. People mess up on antennas all the time. And it's just amazing. People don't want external antennas, they want internal antennas, or they want external antennas, and there's a lot to consider. Return loss, radiation patterns, test environment. There's a lot of things to consider. So you can look at this a little bit later. There's a big move to internal antennas. The problem is there's a lot of there's a lot of differences. So designing with an external antenna, there's a lot of things to consider. The visuar, the amount of basically how you connect to the antenna for the RF path. The visuar voltage standing wave ratio for all those old RF guys. I see a couple in the front row here. But you have to have that right, the impedance patching right for that, and get the right Smith pattern chart of the radiation transmission correct. Same thing happens with an internal antenna, but now with an internal antenna, we tend to be inside of a case, and we have to worry about what's in the case. So here's an example. Tau Glass sent this to me. It's a pretty good example. We can see on the good side there on the left, they have the antenna towards the end. It's pretty much away from all the main components, and it's in a plastic case. The radiation pattern doesn't really have anything really interfering with it. And on the right, they put the antenna up by some plastic, but then below their board they have some metal, because they happen to want the support of the metal case. So part of it's a metal case. Well, now what happens is your radiation pattern, it actually hits the metal and it bounces, and it actually, refracting is light, but it actually bounces back, and it comes back, and it actually can interfere with your antenna. And this actually degrades the amount of reception you're going to have and receive, and it interferes with your transmission. So a lot of bad things can happen. So you really don't want to design it that way. There's ways around this. You can put things like absorbing material on the back plane to absorb the energy so it doesn't reflect back. There's a bunch of things you can do, but yeah, and I see one colleague grimacing, and I agree. It'd be better to design it right the first time and not have these problems. But ONS services, normally no one designs it right the first time. They call us after there's a big problem, and then we go back and we fix it for them. So, internal antenna killers. There's another one. Is probably ground plane links. And I wanted to briefly mention this, and I call this the cheat, the 2 mil dielectric cheat. If anyone has ever read Dr. Howard Johnson's book about embedded capacitance, this is basically saying you have 1 ounce copper, 1 ounce copper, about a max of 2 mil pre-prag in between the two. And this is something that like QC Graphics or a fab house like Global Design could help you with, getting that down right. And when you put them really, really close together, you basically have an embedded capacitor. And now that eliminates a whole bunch of bad noise. The problem is there's all these patents that exist for the 2 mil dielectric. They were owned by Zycon and Hadco, and then Sanmina bought Zycon and Hadco, so now there's Sanmina patents. So if you try to build a board and you specify in your layout that you want a 2 mil dielectric, a fab house, if they do it legally, is supposed to tell you you have to pay this $1.50 patent fee per board that you build. Or you go to Sanmina and they do it for you, right? There's a bunch of antenna examples to look at. These are different things and they're used in different places. Here's a smart thermostat example. I want to talk to you briefly. This is the smart thermostat in question from Honeywell. They sent me to evaluate. It's a nice product. It's voice activated. You can you have it plugged in. You can talk to the thermostat. You can tell the thermostat, make it hotter, make it colder. It's a great product. The one problem is they decided that all the processing for the voice commands would be at the Honeywell server in Minnesota.
Oh boy.
So you say, hello thermostat, and you can watch it processing. You can watch it, you can see, if you have a Wi-Fi sniffer, you can see it going to your access point and then going off someplace else to the Minnesota server, and it processes it, and it comes back and it says, hello, which is, it's a nice voice. And you say, make it colder. And it makes it colder. But the problem is the way I talk, I say, hello thermostat, make it colder. And a minute later it says, hello, and it's ready for you to input the cold or hot command. Well, I've already walked off to do something else. So I wondered why it didn't make the house any colder. They've now fixed this problem with local processing. They have a better, they had an ARM 5 processor in there before. Now they have an ARM 926 processor in there. And now it recognizes it locally. Another problem they had, which was a bummer during our test process, because I had this set up in my house when I was testing it, is it turned out it would key on the word hello anytime I heard the word hello. So I'm watching television, and the television guy says, hello, good morning, America. And the thermostat would say, hello, how can I help you? And then the TV would say, boy, it's hot out here. And the thermostat would make it hotter. And it really blew. So they've now changed this. You can change the sensitivity level, basically the distance of how far away it recognizes the hello thermostat and these other things. So they're getting better. I asked them, well, can I trade this up for the new model? No, you got to buy the new model, but different issue, you know. But medical example. This is a picture of a sleep apnea or CPAP machine. Many of you maybe don't have these. I have one of these at home. Actually, I have that same one at home. And so this is used for people that have breathing disorders. The problem they had is an SD card data storage. And the idea is that you would program this with some information of the settings to set the CPAP machine. And then every time it would turn on, it would look at that card and look at the data. The problem is the designer didn't really think about the fact that an SD card has only so many reads and writes before it starts to fail. So what starts to happen is after you start hitting the max amount of read and writes on that SD card, the machine no longer is able to read the data parameter, and so the machine would start to fail. It would fail way before its manufacturer warranty says it should have been failing. And the simple fix is, okay, you got to reprogram that SD card and stick it in there. But the only people that are allowed to reprogram the SD card is you have to go back to the doctor, make an appointment, and have them reprogram it. And then they don't want to reprogram it, really, because they've actually subcontracted that to another company. And the only way they get paid is if you do another sleep study, which is basically a 12-hour night test to redo it. So it caused a big hassle. So the company that makes this came to us and said, hey, we want to have it on Wi-Fi and just have it controlled, and we want to take the control. Once we program it, it'll be there in NVRAM, and then we can get updates. The doctor can get updates. He can update it on the fly, and so we change that problem. And I want to show this one really briefly. This one I was sent recently of the ResMed. It's the Sleep Better product. It's an interesting product. You put it by your bed at night, and it listens to you breathing. And it gives you some analysis of whether or not, how well you're sleeping. It hooks up by Bluetooth to your Apple iPhone. It's kind of cool. The only problem with it is people didn't think about real-world use, I think. We tested this with a bunch of developers, and a lot of our developers, it turns out, they turn in their sleep. So as soon as you turn away from the machine thinks you stop breathing, and it wants to make an alert that you're suffocating. And this is a problem. So in the morning we get these test results which show that they were breathing fine and then they died in the middle of the night. So so you need to kind of think about how you're designing your medical product for your customer. So they're great products, but security, cybersecurity. We'll wrap up with this here. Cybersecurity is a problem because if you can access this data, they can sell your data, your infotainment data, which could be minorly annoying. They can manipulate traffic data outside the house. They can send an electric vehicle towards your house as a missile to kill you, right? They could, if you have a smart home with home security systems, and they could hack your home security system, they could turn your home into a prison. They could lock you out of your own house. There are now Schlage and Kwikset now have IoT-enabled locks in the home where you can control them with your cell phone. But what if someone else hacks into that and locks you in your house and you can't get out? Right? What if they cut your telephone lines? Right? Now you can't call out, and now you're stuck in your house until you decide to pay some amount of money to let you out of your own house. That could be a bummer, right? Removing safety barriers. I was actually in Vienna giving a lecture on this topic, and one of the large manufacturers, I won't mention who, mentioned to me outside our talk that one of the problems they had was a hacking group got into one of their systems and they disabled the electric vehicle battery charging safety control. And what that did was that enabled that you could actually have the battery plugged in and you could overcharge it, and that battery could actually explode, and the amount of damage would take out your garage and possibly part of your kitchen. So and they've now corrected that problem, but that's a security concern. Even in the house, when we have UPSs in the house, uninterruptible power supplies, those are big battery systems. If you were able to turn off that safety control system, you could have potentially a bomb in one part of your house or other parts of your house. So that could be a problem. There's lots of security that's available. I mentioned dual elliptical deterministic random bit generation. I put it up there as a joke, well, not a joke, but many years ago, NIST recommended using dual EC-DRBG as a recommended security protocol. What they didn't tell you, and what NIST didn't know, was that the NSA had hacked it years before, and they didn't tell anyone except the employees of NSA. And so they're the ones that recommended it to NIST that they include it. And they included it that way if NSA, if they wanted to, any device using this protocol, the NSA could hack it and look at the information. So now everyone kind of knows this now, so pretty much no one uses that encryption method anymore. And NIST finally removed it from their spec after they were embarrassed by another agency. So now there's other protocols. ITripleE is actually working on one now called the Biometric Open Protocol. And they're using the Department of Defense Trusted Computer Security Protocol. The one interesting thing about the BOPS protocol is it also relies on what they call liveness. Not only is it using a biometric imprint, it's using a biometric imprint, and it knows from other information, are you alive? Because you can actually copy someone's biometric data and just use that. But this actually says, the biometric data plus, is the person alive? Is that the person? And not just a heartbeat, but is it your heartbeat? So if you think about it, every person's heartbeat here is different in their rest state, their active state, and it changes. This allows you to have that changing rate about availability attached to your biometric standard. So this makes it much more viable. This talks about that. And we're about out of time, but I want to talk about briefly about 1874. And this is a new standard for a schema for repair of electronic devices. And ITripleE has come up with this. This is a way for you to learn how, for documenting for your customers how to repair their own devices. And for consumers, how to repair their own devices. This makes it into basically an XML format that's easily readable on tablets and PCs and iPhones and Android devices. This actually, it's an open spec, but it's been used now by Dell. It's being used by Ford, by Honda, mostly internally. But this, we see this as the future, being able to repair things. Now, it's an interesting thing. There's a dichotomy. We have the engineers and technicians at all major companies love 1874. VP of sales, all of the upper executives, they hate 1874. No one wants you at an upper level to take your product apart and fix it yourself. They want you to call them and be part of their warranty program and send it in and get money that way. But a lot of companies are using this internally, even just for themselves. Ford uses this internally for their own technicians to be able to repair things on the fly. So you can have it in the vehicle, step-by-step videos showing you how to do it. And all the standard does, it says when you have this video, when you have this audio, how is it displayed in a uniform format so you can use it across multiple devices. Step-by-step how to do this. Interesting enough, this was funded and started by a friend of mine, Kyle Wines from iFixit. They have an interesting website. Shout out to him. You can go there with thousands of free documents how to fix your Mac devices and PlayStations and other things. But this is an interesting standard for you guys to look at. That's my talk. Thank you very much.